the Event Sourcing Anti-Pattern Handbook, Navigating Common Pitfalls and Building Resilient Systems. Chapter 1, The Event Sourcing Journey, Promise, Power, and Pitfalls. 1.1 Introduction. The Allure of Event Sourcing. In the rapidly evolving landscape of modern software development, certain architectural patterns emerge with the promise of transforming how we build resilient, scalable, and insightful systems. Event sourcing ease is undoubtedly one such pattern. You've likely heard the buzz: audit trails by design, time travel debugging, unprecedented scalability, true decoupling, and the ability to gain deep historical insights into business processes. It paints a compelling picture of systems that are not only performant, but also inherently understandable, adaptable, and robust. At its core, event sourcing fundamentally shifts our perspective from storing the current state of data to recording the sequence of events that led to that state. Imagine not just knowing what a customer's current address is, but knowing every address they've ever had, when they changed it, and why. This temporal dimension, coupled with the immutable nature of events, holds immense potential for developers and businesses alike. It offers a clear, auditable log of everything that has ever happened in a system, allowing for powerful analytical capabilities and seemingly effortless reversibility for audits or debugging. The appeal is undeniable, drawing in organizations eager to harness these powerful capabilities. However, like any powerful tool, event sourcing also carries a hidden complexity. Initial enthusiasm, while valid for the promise, often overlooks the intricate challenges and paradigm shifts required for its successful implementation. 1.2 The Double-Edged Sword. Complexity and Challenges. The transition to event sourcing is more than just choosing a new database. It's a fundamental shift in how we think about data, state, and system interactions. It introduces new paradigms that can feel counterintuitive to those accustomed to traditional create, read, update, delete CRUD models. Suddenly, you're dealing with eventual consistency, read models that live separately from your write model, and the unique challenges of replaying historical events. This learning curve, if underestimated, can lead to costly misunderstandings and misapplications. What might seem like a straightforward solution in a CRUD-based system often requires a completely different approach in an event-sourced one. The hidden costs are not just in the initial setup, but in sustained development, operational overhead, and particularly in the pitfalls that arise from applying traditional thinking to a non-traditional problem space. Ignoring these complexities can turn the promise of event sourcing into a source of frustration, technical debt, and system instability. 1.3 Understanding Anti-Patterns. A guide to what not to do. This is where the concept of anti-patterns becomes critically important. In software architecture, an anti-pattern is a common, recurring solution to a problem that paradoxically leads to negative consequences. It's an approach that seems like a good idea on the surface, or arises from ingrained habits, but ultimately causes more harm than good. Think of it as a well-trodden path that, instead of leading to your destination, steers you into quicksand. In the context of event sourcing, anti-patterns are particularly insidious. Because events are immutable facts once recorded, they cannot be changed, or deleted mistakes made in event design or processing become incredibly difficult to unwind. A poorly designed event schema, an incorrectly handled projection, or an excessive amount of inter-service chatter will not only introduce technical debt, but can fundamentally compromise your system's integrity, performance, and long-term viability. The distributed nature of many event-sourced systems means that issues can propagate rapidly, amplifying their negative impact across the entire architecture. Recognizing and understanding these anti-patterns early in your event sourcing journey, or even during an ongoing implementation, is paramount. Avoiding these common traps can mean the difference between building a robust, auditable, and scalable system, and creating a tangled mess of slow performance, data inconsistencies, and operational nightmares. 1.4 Who this book is for and what you'll learn. This book is crafted for software developers, technical leads, and solution architects who are either embarking on an event sourcing implementation or who are grappling with the complexities of an existing one. If you're a product or project manager seeking a deeper understanding of the technical intricacies and potential pitfalls of this architectural style. You will also find valuable insights here. While a basic understanding of software development principles and distributed systems concepts is helpful, this book does not assume prior specialized knowledge of event sourcing. Chapter 2 will provide a concise, accessible refresher on the core concepts, ensuring everyone is on the same page before we delve into the common mistakes. Our aim is to provide practical, actionable advice, moving beyond mere theory. You will learn to identify the most common event sourcing anti-patterns, understand the root causes and detrimental consequences of each anti-pattern, discover concrete strategies and best practices to avoid or mitigate these pitfalls effectively, gain clarity on how to design event-sourced systems that are truly resilient, scalable, and maintainable. The journey through this book will first anchor you in the fundamental concepts of event sourcing, then systematically expose you to the most prevalent anti-patterns, followed by clear, actionable solutions. 1.5 The Philosophy: Building Resilient Systems. Ultimately, this book is about more than just avoiding errors. It's about cultivating a mindset that leads to the creation of truly resilient, adaptable, and maintainable software systems. Event sourcing, when applied thoughtfully and correctly, offers unprecedented opportunities for clarity, scalability, and deep insight into your business operations. It demands a shift in perspective, from managing mutable state to understanding a stream of immutable facts. It requires embracing eventual consistency and designing for failure. By dissecting the common missteps and providing pathways to healthier implementations, this guide empowers you to move beyond the pitfalls and unlock the profound benefits that event sourcing promises. Let's embark on this journey to build systems that not only work but endure and evolve gracefully. Chapter 2: Event Sourcing Reimagined. Core Concepts for the Discerning Architect. Before we dive into the common pitfalls of event sourcing, it's essential that we establish a clear and shared understanding of its foundational concepts. For some, this chapter might serve as a refresher. For others, it will lay the groundwork for a new way of thinking about data and system behavior. Our goal is to provide a concise yet comprehensive overview, emphasizing the principles that are most crucial for avoiding the anti-patterns discussed later. 2.1 Events as Facts: The Foundation of Event Sourcing. At the heart of event sourcing lies the concept of an event. Unlike traditional databases that store the current state, e.g., a customer's current address, event sourcing records every significant action or change that has ever occurred within your system. What is an event? An event is an immutable past tense fact about something that happened in your business domain. It directly translates a business occurrence, such as order placed, customer registered, payment received, or inventory adjusted. Once an event has occurred and been recorded, it can never be changed or deleted. It's a statement of truth about the past, a historical record. Think of it like a meticulous accounting ledger, a ship's logbook, or a personal diary. In a traditional database, you might simply update a balance, overwriting the previous value. In an event-sourced system, you record debit of $50 and credit of $100. The current balance is then derived by replaying these transactions. Similarly, for a customer's address, you don't just update the address field. You record an address changed event. This event contains the details of the change, and the customer's current address can always be determined by applying all historical address-related events in order. This immutable, chronological sequence of facts is what makes event sourcing so powerful, offering an unparalleled audit trail and the ability to understand history. 2.2 The Event Store. The append-only ledger. If events are the facts, then the event store is where these facts are meticulously recorded. Its primary role is to serve as a persistent, ordered, and immutable log of all events that occur within your system. Events are always appended to the store. They are never updated or deleted. The event store is not a general-purpose database in the traditional sense. You don't perform complex queries, joins, or arbitrary updates on it. Its optimization is for two main operations: appending events, recording new facts quickly and reliably; reading event streams, retrieving a sequence of events for a specific entity, like an order or a customer, in chronological order. This append-only nature provides several profound benefits. Single source of truth. The event store becomes the definitive record of all system activity. If the rest of your system were to vanish, you could rebuild its entire state from the events in the store. Robust audit trail. Every business decision and data change is recorded, providing an unbreakable chain of actions. This is invaluable for compliance, debugging, and understanding system behavior. Replayability. The ability to replay historical events opens doors for debugging, data migration, and even building new features by processing past data in novel ways. Understanding that the event store is a specialized ledger, not a relational database for arbitrary queries, is critical to avoiding many anti-patterns. 2.3 Aggregates. The guardians of business rules. While events are the atomic facts, systems need a way to ensure business rules are applied consistently and modifications occur in a principled manner. This is where the concept of an aggregate comes into play, a core idea borrowed from domain-driven design, DDD. An aggregate is a cluster of domain objects that are treated as a single unit for data changes. It acts as a transactional boundary. This means that within a single business operation, all changes must happen within the confines of one aggregate. You can't start a transaction on one aggregate and finish it on another. This ensures that the invariant consistency rules of your domain are maintained. When a command arrives, an instruction to do something, like place order or change customer address, it is dispatched to the relevant aggregate. The aggregate then loads its current state by replaying all its historical events from the event store. Based on this reconstituted state and the incoming command, the aggregate applies business logic, validates constraints, and if successful, emits one or more new events. These new events are then appended to the event store, marking the completion of the business operation. The aggregate serves as the gatekeeper, ensuring that only valid and consistent changes lead to new events being recorded, making it the primary entity responsible for applying business rules and maintaining the system's integrity. 2.4 Projections, read models, optimizing for queries. If the event store is your audit trail and your aggregate is where business rules are enforced, how do you efficiently query the system for current state? Attempting to query the raw event store for complex data would be incredibly slow and inefficient, as it's optimized for sequential reads of specific streams, not arbitrary lookups. This is where projections, also known as read models, become indispensable. This concept is closely tied to command query responsibility segregation, CQRS, a pattern that separates the responsibility for handling commands, writes, from the responsibility for handling queries, reads. Projections are dedicated, denormalized views of your data that are optimized specifically for querying. They are built by consuming events from the event store. When an event is appended to the event store, it is then published to various projection handlers. Each handler processes the event and updates its corresponding read model, which can be stored in any type of database, e.g., a relational database for complex queries, a NoSQL document database for flexible schemas, or a search engine for text search. Since read models are built by processing events asynchronously, they might temporarily lag behind the very latest state in the event store. This is known as eventual consistency. While the event store is always the absolute source of truth, read models provide highly performant, tailored views for different user interface needs or reporting requirements. For example, an order-placed event might update a customer dashboard read model, showing recent orders in a relational database, and simultaneously update a daily sales report read model in an analytics database. 2.5 Event handlers and subscribers, reacting to changes. Once events are emitted by aggregates and stored in the event store, the system needs mechanisms to react to them. This is the role of event handlers and subscribers. An event handler is a piece of code that listens for specific types of events and performs a defined action or update based on that event. For instance, when an order-placed event occurs, an order confirmation email sender handler might send a confirmation email to the customer, while an inventory updater handler might decrement stock levels. The underlying mechanism for this is often a publish-subscribe pattern, where events are published to a messaging system, like a message queue from the event store, and various subscribers register their interest in specific event types. This promotes significant decoupling between different parts of your system. The component that produces the event doesn't need to know who consumes it. A critical property of well-designed event handlers is idempotency. This means that processing the same event multiple times should produce the same result as processing it just once. Given that message delivery systems often guarantee, at least once, delivery, meaning an event might be delivered more than once, designing handlers to be idempotent is crucial for system reliability and consistency. We will delve much deeper into this important concept in a later chapter. 2.6 Advantages of event sourcing when done right. When implemented correctly, event sourcing delivers on its promise, offering a range of compelling advantages. Robust audit trails. Every tiny change and business decision is captured as an immutable event, providing a complete historical record. Simplified debugging and time travel. The ability to replay events allows developers to reconstruct the system's state at any point in time, making it easier to diagnose issues or even rewind to understand past scenarios. Improved scalability and decoupling. The append-only nature of the event store can support very high write throughput. Events act as the sole language of communication between components, fostering loose coupling and allowing services to evolve independently. Better understanding of domain behavior. The process of identifying and modeling business events forces a deep understanding of the domain, leading to more accurate and expressive software. Facilitates complex analytical queries. Historical events are a rich dataset for analytics, machine learning, and business intelligence, allowing you to ask questions about what happened over time, not just what is. Easier refactoring. Because business logic is centered around commands and events, rather than mutable state with complex dependencies, refactoring can be safer and more contained. 2.7 Common misconceptions to clear up early. Before we proceed, let's dispel a few common misunderstandings that can trip up even experienced architects. Event sourcing is not just a message queue. While it often uses message queues to publish events, its core is about durable event storage as the primary data source, not just transient message passing. Event sourcing is not only for microservices. While it complements microservices architectures well due to its emphasis on decoupling, event sourcing can be applied effectively within monolithic applications or other architectural styles. Event sourcing is not a fire-and-forget system. It requires careful design, particularly around event modeling, versioning, and managing eventual consistency. Ignoring these complexities leads directly to the anti-patterns we will explore. Event sourcing is a paradigm shift, not just another tool. You cannot simply layer it onto an existing CRUD mindset. It demands fundamental changes in how you perceive data flow, state management, and interaction between system components. With these foundational concepts in mind, you are now equipped to understand why certain common approaches in event sourcing can lead to difficult architectural and operational challenges. Let's move on to explore those pitfalls. Chapter 3, The Mono Event, when every tiny change becomes an event. Having established a solid understanding of event sourcing fundamentals, we now turn our attention to the first prevalent anti-pattern, the mono event. This pattern, characterized by an overemphasis on atomic, low-level data changes as events, can severely undermine the benefits of event sourcing and lead to significant operational and design challenges. 3.1 What is the mono-event anti-pattern? The mono-event anti-pattern occurs when developers generate an event for virtually every single, granular property change within an entity. Instead of modeling events that represent meaningful business actions, the system emits events like user first name changed, user last name changed, user email changed, or even product price updated and product description updated as separate, distinct events. Consider a user updating their contact information. In a mono-event scenario, you might see a sequence of events such as user first name changed, payload, userid, ABC, old first name, John, new first name, Jonathan, user last name changed, payload, userid, ABC, old last name, Doe, no last name, Smith, user email changed, payload, userid, ABC, old email. johndoe@example.com, new email, jonathansmith@example.com. Contrast this with a more business-centric approach, where a single event like user contact information updated, payload. User ID, ABC, new first name, Jonathan, new last name, Smith, new email, jonathansmith@example.com, changed fields, first name, last name, email, encapsulates the entire change. The mono event mistakenly equates an event with a data field change. A direct carryover from traditional CRUD, create, read, update, delete thinking, where every individual field modification is registered. In an event source system, however, events are meant to represent what happened from a business perspective, not just what data changed. 3.2 Symptoms and Consequences. The seemingly granular and auditable nature of mono events often masks a plethora of problems. Explosion of event types. Your event catalog quickly becomes unmanageably large, with countless specific event types like order quantity changed, order discount applied, shipping address changed, etc. This leads to configuration headaches, a complex event schema registry, and a higher cognitive load for developers trying to understand 50 different ways an order can be updated. Event volume storms. Every minor modification generates new events. Imagine updating a user profile with 5 different fields. That's 5 distinct events instead of 1. In high-traffic systems, this translates into a massive volume of tiny events, overwhelming your event store, messaging infrastructure, and downstream consumers. Performance degradation on reconstitution. Aggregates load their state by replaying all historical events. If an aggregate's history is composed of thousands of tiny mono events, reconstituting its state becomes a slow and computationally expensive operation. The larger the event stream, the longer it takes to rebuild the current state. Loss of business context and meaning. While individually auditable, a stream of mono events often obfuscates the higher-level business narrative. What exactly happened when user first name changed, user last name changed, and user email changed events occurred in quick succession? It's harder to grasp that a single user contact information updated business operation took place. This semantic noise makes event streaming analytics, debugging, and understanding system behavior significantly more difficult. Increased storage costs. Many small events often lead to more overhead per event, e.g., metadata, timestamps, header information, compared to fewer larger events, potentially increasing storage consumption. Complex replay and debugging. Replaying a long sequence of granular events is cumbersome. Debugging an issue involves sifting through a much larger and less meaningful event stream. 3.3 Root causes of this anti-pattern. The mono-event anti-pattern typically stems from a few common misunderstandings or ingrained habits. Mistaking event for data change notification. This is perhaps the most fundamental misunderstanding. Developers treat events as passive notifications of data alterations rather than active declarations of a completed business fact. This is a direct conceptual migration from MVC or traditional data-driven development. Overemphasis on fine-grained auditing. The desire to audit every single field change, under the guise of getting all the detail, leads to the belief that every field change must be its own event. While the event store does provide a detailed audit trail, the events themselves don't need to be that granular to achieve it. Fear of losing detail. Developers worry that if they combine multiple data changes into a single event, they might lose specific information about which fields changed. This can be mitigated by including a changed fields array or similar construct within the richer business event. Inherited habits from CRUD-based thinking. Because we often interact with data at a field level in UI forms or database tables, it's natural to map this directly to events. However, the business world rarely operates at such a minute level of detail. It performs logical operations like update profile. Lack of deep domain understanding. Without a clear understanding of the business domain, it's harder to identify meaningful business actions versus mere data mutations. 3.4 Strategies to avoid the mono event. Avoiding the mono event anti-pattern requires a conscious shift in perspective and a focus on modeling business behavior. Focus on business intent. Events should represent a completed business action, not merely a data change. Ask what happened. not what changed. Instead of customer first name changed, think customer name updated. Instead of order quantity changed, think order line item adjusted, which would encapsulate the specific item and new quantity. Instead of payment amount adjusted and payment status changed, think payment refunded or payment failed. Model events at the right level of granularity. There's a sweet spot between too many tiny events and too few large ones. The right granularity corresponds to a logical unit of work from a business perspective. Use techniques like event storming or user story mapping collaboratively with domain experts. These workshops help visualize and identify the true business events that drive your system. Events should typically be derived from the outcome of a command processed by an aggregate. If a command, e.g., change address, results in multiple field updates, street, city, zip, one address changed event is usually sufficient. Combine related data changes into a single meaningful business event. If multiple data fields are updated as part of a single, atomic business operation, represent it as one cohesive event. The event payload can then contain all relevant new and, optionally, old values for the fields critical to understanding that change. Use aggregates correctly to ensure atomicity. The aggregate pattern helps enforce consistency boundaries. If an operation changes multiple attributes within an aggregate, those changes should be encapsulated within one set of events that are committed atomically. This reinforces the idea of a single business transaction yielding a single business outcome. Even if that outcome is reflected in multiple events, they derive from the same atomic action. Understand different types of events. Not all events are equal. Domain events, what happened within a bounded context, are distinct from integration events. What happened that other bounded contexts need to know about? The granularity might differ, but the principle of business intent remains. 3.5 Case Study Anecdote: the overly chatty customer service system. Consider a company, Service Central, building a new customer management system using event sourcing. Their initial design team, coming from a strong transactional background, decided that every single field update in a customer's profile should generate its own event. So, changing a customer's name, email, and phone number would result in customer name changed, customer email changed, and customer phone number changed events being logged sequentially. Consequences: performance bottlenecks. Customer service representatives reported that opening a customer's profile was agonizingly slow. The system had to replay hundreds, sometimes thousands, of tiny events to reconstruct the customer's current state. This became especially problematic for long-standing customers with many historical changes. Overwhelmed analytics. The analytics team found it almost impossible to glean meaningful insights from the event stream. They wanted to know when a customer's contact information was last updated, but instead they had a flood of individual field changes, making it hard to detect the logical grouping. Debugging nightmare. When a customer's profile appeared incorrect, tracing the issue through a myriad of granular events was a debugging nightmare, often requiring manual reconstruction of the sequence to understand the logical flow. High event store volume. The sheer volume of events consumed excessive storage and placed high write load on the event store. Resolution. The team realized their mistake during a performance audit. They redesigned their event model to focus on business intent. Instead of individual field-level events, they introduced customer personal information updated for name, date of birth. Customer contact information updated for email, phone, address. Customer status changed, e.g., customer activated, customer suspended. These new events contained all the relevant new values for the grouped fields. The historical customer name changed events were still there, but any new changes generated the consolidated events. This significantly reduced event volume, sped up aggregate reconstitution, and made the event stream vastly more readable and useful for analytics. The customer service portal became responsive, and the technical team regained confidence in their event sourcing implementation. 3.6 Key Takeaways for Event Granularity. The mono-event, anti-pattern, is a common trap that highlights a fundamental mismatch between traditional data-centric thinking and the event sourcing paradigm. To avoid it, always remember, Events communicate what happened in the business domain, not just what data changed. Prioritize conceptual clarity and business meaning over atomic data fidelity in your event definitions. The right granularity is a balance. It represents a completed business fact that is meaningful to consumers without being overly generic. Aim for events that tell a story, not just list data modifications. Chapter 4. The big event, loss of context and overabstraction. In the previous chapter, we explored the pitfalls of the mono event, where events are too granular, representing individual field changes rather than meaningful business actions. Now, we swing to the opposite end of the spectrum with another equally detrimental anti-pattern, the big event. This anti-pattern involves creating events that are overly broad, generic, or encapsulate too much disparate information, often leading to a loss of context and unnecessary coupling. 4.1. What is the big event anti-pattern? The big event anti-pattern manifests when events are designed to be excessively comprehensive, generic, or loaded with data that isn't directly relevant to the specific business fact they're meant to convey. Common examples include overly generic event names. Something happened, entity updated, generic data changed, item modified. These names are so vague that they convey little to no useful information about the business action that took place. Massive payloads. Events that carry an excessive amount of data, often entire entity graphs, even if only a small fraction of that data changed or is relevant to the event's purpose. For instance, an order updated event that includes every single detail about the customer, all products in their cart, their payment history, and their address, even if only the shipping status changed. Combining unrelated concepts. An event trying to capture multiple, distinct business facts within a single message. Imagine user product updated, which is clearly trying to do too much. This anti-pattern often arises from a desire to be future-proof or to simplify the number of event types, but in practice, it achieves the exact opposite. It's like a newspaper headline that just says news, or a summary of a meeting that includes every single word said by every participant rather than the key decisions. 4.2. Symptoms and consequences. The alluring simplicity of fewer, more generic events quickly turns into a complex nightmare. Lack of clarity for consumers. When a something happened event arrives, downstream consumers have no immediate clue what happened. They are forced to inspect the entire large payload and apply complex conditional logic to infer the actual business intent. This makes event-driven architectures difficult to understand and maintain. Tight coupling. Because events carry broad, often irrelevant data, consumers become implicitly coupled to the entire schema of the large event. If one field within that massive payload changes, it might trigger a ripple effect of changes across many consumers, even those that don't care about that specific field. This undermines the very decoupling that event sourcing aims to provide. Schema evolution nightmares. Evolving a large, multi-purpose event schema is profoundly difficult. Any change to the event structure, no matter how minor, might impact numerous consumers. This either leads to extensive coordination efforts or, more commonly, fear of change and a reluctance to evolve the system. Inefficient message passing. Sending massive event payloads across the network consumes excessive bandwidth and processing power. This is particularly problematic in distributed systems where network latency and throughput are critical concerns. It's like sending a whole library when a single book would suffice. Replay difficulties and debugging. Large, generic events can make event stream replay more challenging, especially when combined with schema versioning. Debugging becomes harder when you lack clear insights into the specific business action being represented in the event history. Blurred intent. When an event fires, it's unclear what specific business operation it signifies. This can lead to misinterpretations and incorrect actions by downstream services. 4.3 Root causes of this anti-pattern. The big event anti-pattern often originates from fear of creating too many event types. This is the inverse problem of the mono event. Developers try to consolidate events to reduce the perceived complexity of managing numerous types. However, this often shifts the complexity from event type management to event content parsing and interpretation. Lack of domain understanding abstraction. A superficial understanding of the business domain can lead to an inability to identify the distinct, meaningful events. Instead of digging deep, developers resort to generic, catch-all events, treating events as data transfer objects, DTOs, for state synchronization. If events are seen merely as a mechanism to transmit the entire current state of an entity, rather than as a declaration of a business fact, then large comprehensive payloads become the norm. This thinking often comes from a background of building CRUD APIs where entire entities are passed around. Developer laziness or future-proofing attempts. Sometimes, it's an attempt to avoid decision-making. I'll just put everything in there so I don't have to add it later. This often backfires, as future changes become harder, not easier. 4.4 Strategies to avoid the big event. To steer clear of the big event anti-pattern, focus on precision, purpose, and lean communication. Specificity and focus. Each event should represent a single, well-defined business fact that can be clearly named. Instead of entity updated, use product name changed or order shipped. Instead of customer and account modified, use customer registered and bank account opened as distinct events. Just enough information principle. Include only the data that is directly relevant to what happened and what essential consumers need to react. If consumers need more information about the entity, they should query a dedicated read model, e.g., using the entity ID provided in the event, or use an API. Events are for facts, not for carrying full entity snapshots. Example, an order-placed event should contain the order ID, customer ID, total amount, and perhaps a list of line items, product ID, quantity, price. It should not contain the customer's full address book, historical orders, or payment details, unless those were intrinsically part of the order-placed event in a very specific scenario. Precise naming. Event names should be verbs in the past tense and clearly communicate the business intent. They should be part of the ubiquitous language of your domain. Decompose complex events. If an initial thought for an event seems to encompass multiple, distinct business facts, consider if it can be broken down into smaller, more focused events. Ask, does this event inherently change multiple distinct aspects of the domain that could be represented as separate facts? Leverage domain-driven design, DDD, concepts. Strong bounded contexts naturally guide event design. Events published between bounded contexts should be concise and focused on the facts necessary for integration, not internal details. Events within a bounded context still benefit from concise design, but expose more internal nuances. 4.5 Case Study Anecdote. The update event in an e-commerce system. An e-commerce company, ShopSmart, adopted event sourcing for its new order management system. Their initial design included a single, overarching event called Order State Changed. This event was intended to capture every possible modification to an order, from adding a product to changing the shipping address, applying a discount, or marking it as shipped. The payload of this Order State Changed event was enormous, essentially containing a full snapshot of the entire order object, including all customer details, items, prices, discounts, shipping information, and payment status, regardless of what actually changed. Consequences: consumer confusion, downstream services, e.g., shipping, analytics, customer support, had to subscribe to this single Order State Changed event. Each service then had to parse the massive payload, identify the specific fields that had actually changed, often by comparing old and new values, and apply complex conditional logic to determine if they needed to react. This was error-prone and difficult to maintain. Tight coupling. A change to any field within the Order State Changed events, payload, even an irrelevant one for a particular consumer, meant that all consumers had to be updated and redeployed, creating a distributed monolith. Performance hit. Publishing and processing, these huge events consumed significant network bandwidth and CPU cycles across the entire system. Disk space for the event store also rapidly became a concern. Schema evolution paralysis. Introducing a new field into the order object, e.g., gift wrap option, meant modifying the order state change schema, which triggered a wave of fear and extensive coordination across all subscribing teams. Resolution. ShopSmart realized their approach hindered agility. They refactor their event model to use specific, intent-driven events: order placed, order line item added, order line item removed, order shipping address changed, order discount applied, order shipped, order canceled. Each of these events contained only the minimal data necessary to convey that specific fact. For example, order shipping address changed only held the order ID and the new shipping address details, nothing about payment or products. This change drastically reduced event size, clarified intent for consumers, they subscribed only to the events they cared about, and loosened coupling across the microservices. Teams could now evolve their functionalities with greater independence, and the system became far more performant and maintainable. 4.6 Key takeaways for event clarity. The big event anti-pattern undermines the very benefits that event sourcing promises: decoupling, clarity, and ease of evolution. To avoid this trap, events are contracts that communicate clear, specific business intent. Think from the perspective of event consumers. What minimal information do they need to react effectively? Prioritize specificity and clarity in event naming and payload design. This enhances understanding, reduces coupling, and simplifies system evolution. Resist the urge to create generic catch-all events. They only defer and amplify complexity. Chapter 5. The Chatty System, Overly Coupled and Fan-Out Failures. Having discussed event granularity, we now move to an anti-pattern that examines the flow and volume of events across system boundaries. The Chatty System. This anti-pattern can emerge even when individual events are well-designed, avoiding both mono-events and big events. When event-sourced services communicate too frequently, too synchronously, or without clear boundaries, the result is a fragile, tightly coupled system that behaves like a distributed monolith. 5.1 What is the Chatty System anti-pattern? The Chatty System anti-pattern describes an event-sourced architecture where services or components engage in excessive, often unnecessary, inter-service communication via events. Instead of using events as asynchronous notifications of completed facts across well-defined boundaries, they are employed for continuous, fine-grained synchronization, or for attempting to orchestrate complex, pseudo-synchronous workflows. Imagine a group of people trying to have a conversation. Instead of brief, focused exchanges, everyone shouts their every thought, creates constant chatter, and waits for immediate responses before continuing their own tasks. This leads to noise, confusion, and a breakdown of effective communication. In a software system, this translates to excessive event traffic. A high volume of events constantly flowing across service boundaries, much of it redundant or too granular for actual cross-service needs. Tight coupling through event schemas. Services becoming implicitly dependent on the minute internal details or specific sequence of events from other services. Complex distributed workflows. Attempting to implement long-running, multi-step business processes through a chain of closely coupled event publications and reactions, often requiring complex sagas or process managers that become brittle orchestration hubs. Fan-out failures. An event published by one service triggers a cascade of events or actions in many others, amplifying any slowdowns or errors. 5.2 Symptoms and Consequences. The consequences of a chatty system are severe and undermine the very benefits of distributed architectures. High network latency and bandwidth consumption. Constant event floods overwhelm network infrastructure, introducing significant latency and increasing operational costs. Distributed monolith. Despite being decomposed into services, the system behaves like a single, monolithic application. Changes in one service require widespread coordination across many others due to tight event schema coupling or intricate workflow dependencies. Independent deployment, a key microservices benefit, becomes impossible. Cascade failures. A slowdown or failure in one service that emits many events can quickly lead to backlogs, timeouts, and failures in subscribing services, as the issue cascades through the event streams. Complex orchestration and sagas. Implementing sophisticated business processes that span multiple services, e.g., an order fulfillment workflow, quickly devolves into complex, hard-to-manage sagas or process managers. These often become centralized bottlenecks and single points of failure. Difficulty tracing. Following the flow of a business transaction through a labyrinth of fine-grained, inter-service events becomes incredibly challenging. Debugging and root cause analysis are significantly hampered. Operational complexity, deploying, monitoring, and debugging such systems become a nightmare. Scaling one component might not help if upstream or downstream components are bottlenecks due to excessive chatter. 5.3 Root causes of this anti-pattern. The Chatty system anti-pattern typically arises from poorly defined bounded contexts. This is arguably the most significant cause. If system boundaries, services, microservices, don't align with clear, consistent bounded contexts from domain-driven design, then components interact without a common language or clear ownership, leading to excessive communication needs. Misinterpreting eventual consistency. Developers might over-index on eventual consistency, believing that every piece of information needs to be immediately propagated everywhere via events. While eventual consistency is fundamental, it doesn't mean constant, immediate synchronization of all data. Attempting synchronous transactions with asynchronous events. Trying to achieve ACID-like properties or tightly coordinated distributed transactions using asynchronous events. Events are best suited for informing about completed facts, not for driving synchronous multi-service operations. Lack of clear API contracts for event consumers. When events are thrown over the wall without a clear contract of what they mean and what specific actions they enable, consumers oversubscribe or try to infer too much, leading to unnecessary chattiness. Defaulting to broadcast all events. Setting up a publish-subscribe system where every event is essentially broadcast to every potentially interested party, instead of targeting specific, relevant consumers. Over-orchestration. Believing that complex business processes require a central orchestrator that dictates every step, rather than allowing services to react autonomously and choreograph their own behavior. 5.4 Strategies to avoid the Chatty system. Avoiding the Chatty system requires a disciplined approach to service boundaries, communication patterns, and embracing true asynchronous behavior. Strong bounded contexts are paramount. Events should primarily serve as concise, public notifications of completed facts that need to be shared between different bounded contexts. Internal events within a single bounded context can be handled synchronously or through internal messaging without crossing network boundaries unnecessarily. They are implementation details. Clearly define what information needs to be shared across contexts and what remains internal. Embrace true asynchronicity and eventual consistency. Do not attempt to use events to achieve tightly coupled, synchronous distributed transactions. Events are for notification of facts, typically used for long-running processes or for projections. Accept that data in different services might be temporarily out of sync. Design your system and user experience around this reality. Orchestration versus choreography, strategic choice. Prefer choreography for simpler interactions. Services react autonomously to events published by others. X publishes an event, Y reacts, Z reacts to Y's event. This simplifies individual services and avoids central bottlenecks. Use orchestration, sagas judiciously for complex, long-running business processes. If a multi-step process requires compensation, undoing previous steps if a later one fails, a saga pattern, often driven by a dedicated process manager, might be necessary. However, keep sagas lean, focused, and only trigger them for state changes that truly warrant cross-service coordination. Minimize cross-context data flow. Ensure that public events, those shared across bounded contexts, contain only the minimal, essential data. If a consuming service needs more detail, it should query the publishing service's API, a command query interaction, after receiving the event, rather than expecting the event itself to carry all possible data. This is often referred to as event-driven architecture with data pulling. Avoid distributed transactions. Realize that distributed ACID transactions are prohibitively complex and introduce tight coupling. Embrace the looser consistency model and design for idempotency and compensation mechanisms to manage eventual consistency. Leverage read models as local caches. Services can build their own local read models by subscribing to public events originating from other bounded contexts. This local caching reduces the need for constant, real-time queries across service boundaries. For example, an inventory service could build a local read model of product information from events published by a product catalog service, rather than querying the product catalog every time an order is processed. 5.5 Case study anecdote: the e-commerce checkout flow gone wild. Fast Cart, an online retailer, decided to implement their new checkout process using microservices and event sourcing. Every single granular step in the checkout process, from adding an item to the cart, changing quantity, applying a discount, all the way to clicking Place Order, published an event. For instance, item added to cart, quantity changed in cart, discount applied to cart, shipping address selected, payment method selected, and every service inventory, promotions, shipping, payment, order fulfillment subscribe to all these events, trying to keep their own internal representation of the cart state updated in real time. Consequences: performance hit. As customers navigated the cart, the system was flooded with events. This led to high network latency, backlogs in message queues, and slow responses. The place order button often timed out because the system was trying to reconcile a constantly changing, highly chatty distributed cart state. Distributed monolith. While they had many microservices, they were all so tightly coupled by subscribing to every granular cart event and trying to keep their state perfectly synchronized that it felt like one giant, slow application. Deploying a change to how discounts worked, for instance, required careful synchronization across half a dozen teams. Debugging nightmare. Pinpointing why a particular order had issues was like tracing a single thread through a million needles. The event stream was a fire hose of granular changes, making it impossible to reconstruct logical flows quickly. Resolution. Fast Cart fundamentally redesigned its approach. They established a clear checkout bounded context. This context handled all the internal nuances of cart state management. It communicated with other services only for critical, committed business facts. Instead of item added to cart, the checkout service would only emit an order-initiated event once the user confirmed their selection. Instead of discount applied to cart, the checkout service would finalize and emit an order-placed event. This order-placed event then contained the final, consolidated state required by downstream services inventory, payment, shipping. Downstream services would subscribe only to order placed and consume minimal information from it, then pull any remaining necessary data via a dedicated API only when needed. This drastically reduced interservice chatter, simplified the event model, and allowed the checkout service to manage its own internal state efficiently without burdening the entire system. Their system became genuinely decoupled and scalable. 5.6 Key takeaways for system decoupling. The Chatty system, anti-pattern, underscores a crucial point. Event sourcing offers powerful decoupling, but it doesn't happen automatically. You must design for it. Events are powerful integration points, but their misuse leads to tighter, not looser, coupling. Design for autonomy and clear boundaries between services, guided by well-defined bounded contexts. Prioritize reducing interservice communication. Only share events that represent significant, committed business facts that another context genuinely needs to know about. Embrace eventual consistency and avoid trying to replicate synchronous transaction models with asynchronous events. Chapter 6. Projections Gone Wild. The Query Model Conundrum. We've covered how to properly model events and manage their flow between services. Now, let's turn our attention to the red side of event sourcing, specifically projections, also known as read models. While projections are indispensable for efficient querying in an event-sourced system, their misapplication can lead to one of the most frustrating anti-patterns: projections gone wild, resulting in inconsistent data, performance issues, and an inability to trust the system's current state. 6.1 What is the projections gone wild anti-pattern? The projections gone wild anti-pattern occurs when projections are not idempotent. Processing the same event multiple times yields different and incorrect results. This is fatal in event-sourced systems where message delivery guarantees are often, at least once, meaning events might occasionally be redelivered. Projections embody complex, non-deterministic logic. The logic used to build the read model is overly complicated, has side effects, relies on external mutable state, or produces different results depending on factors outside the event itself, e.g., system clock, order of external calls. Projections are tightly coupled to specific event versions or internal schemas. Any change to an event schema requires a complete rewrite of the projection, making schema evolution incredibly painful. Projections are not designed for rebuilds. The process of dropping and recreating a read model from the event store is either prohibitively slow, error-prone, or simply not considered, leading to data staleness or corruption over time. Imagine trying to keep a detailed, indexed library catalog perfectly updated. If the librarian sometimes adds duplicate entries for the same book, or alphabetizes books differently based on what time of day they're put on the shelf, or forgets to update the index when a book is moved, the catalog quickly becomes useless. This is analogous to a projection gone wild. 6.2 Symptoms and Consequences. The fallout from this anti-pattern can be severe, impacting data reliability and system maintainability. Data inconsistencies. The most obvious symptom. Read models frequently show incorrect, outdated, or duplicate data compared to the true state derivable from the event store. Customers see wrong order statuses, inventory counts are off, or analytical reports are inaccurate. Manual correction loops. Operations teams find themselves constantly running manual database cleanup scripts or hacks to align the read models with the real state, indicating a fundamental flaw in the projection logic. Inability to rebuild. When a read model becomes corrupted or a new projection is implemented, the process of rebuilding it from the entire event stream is either impossibly slow, fails repeatedly, or yields inconsistent results. This undermines one of the core benefits of event sourcing, the ability to rebuild state from immutable facts. Slow queries operations. While projections are supposed to optimize reads, poorly designed ones can themselves become bottlenecks if the projection process is inefficient or the resulting read model is not properly indexed for queries. Debugging nightmares. Tracing data inconsistencies back to a faulty projection is extremely difficult, especially if the projection logic is opaque or its state is non-deterministic. Fragile logic. Projections become a spaghetti of if-then-else statements, trying to account for all possible event sequences, version changes, and external factors, making them hard to test and maintain. 6.3 Root causes of this anti-pattern. Projections gone wild largely stems from a misunderstanding of the projection's role and the guarantees required for handling mutable state in an eventually consistent world. Treating projections as just another view. Developers approach projections with a traditional database view mindset, where the underlying data is always consistent. They fail to account for asynchronous event processing, potential redeliveries, and the need for idempotency. Lack of focus on idempotency. This is a key culprit. Assuming events will be delivered exactly once leads to projection logic that only works correctly on the first processing of an event, not designed for rebuilds. The assumption that once a projection is built, it will run forever without needing a rebuild. This leads to projections accumulating bad data over time or being unable to adapt to schema changes. Pushing business logic into projections. Some developers mistakenly put complex business logic, which should reside in the aggregate on the right side, into projections. Projections should be about data transformation for query optimization, not business rule enforcement. Reliance on external mutable state. Projections might try to factor in data from external systems or caches that are not derived from the event stream itself, leading to non-deterministic outcomes during replay or rebuild. Insufficient testing. Failing to rigorously test projections with various event sequences, duplicate events, and full rebuild scenarios. 6.4 Strategies to avoid projections gone wild. To build robust, reliable, and trustworthy read models, adhere to these core principles. Idempotency is paramount. This is the most crucial rule for any event handler, especially projections. A projection must produce the very same read model state if an event is processed one time or 100 times. Techniques for idempotency. Unique event IDs. store the unique ID of the last event processed by the projection. If a duplicate event arrives and its ID is already recorded, simply ignore it. UPSERT operations. When creating or updating records in the read model, use UPSERT, update or insert operations if your database supports it. This updates a record if it exists or inserts it if it doesn't, making the operation repeatable. Conditional updates. For specific fields, implement logic that only applies the update if the current value is different, or if a version number on the read model record matches the expected version from the event. Focus on state-based updates. Projections are typically about updating a current state in a read model. Think set and UPSERT rather than increment if you are not carefully tracking what has been applied. Design for rebuilds. Always assume that any read model might need to be dropped and completely rebuilt from the entire event stream stored in your event store at any given time. This implies that all necessary information must be present in the historical events. Avoid storing transient external data within the read model that cannot be re-derived from events. Invest in tools and processes for efficient read model rebuilds, e.g., parallel processing frameworks. Strict separation of concerns, write model aggregates. This is where your core business logic, invariance, and command validation reside. Aggregates produce events. Read model projections. These should be purely about transforming event data into an optimized query structure. No business logic should live in your projection handlers. Projections should be dumb data processors. Optimize for read scenarios. Design projections specifically for the queries they will serve. Avoid creating monolithic, generic read models. If you have different query needs, create multiple, specialized projections. This often means denormalizing data heavily in the read model for performance. Simplicity and determinism. Keep projection logic as simple and deterministic as possible. Avoid external dependencies, side effects, or reliance on system clock within projection logic that would make them non-deterministic during replay. Rigorous testing of projections. Unit test projection handlers. Test their transformation logic in isolation. Integration test with event sequences. Feed a series of events, including duplicates and out-of-order events, if applicable to your messaging guarantees, and assert the correctness of the resulting read model state. Test the full rebuild process. Verify that a full rebuild from your event store consistently produces the expected read model. 6.5 Case Study Anecdote. The customer dashboard that was always wrong. ConnectCo, a telecommunications provider, implemented a customer dashboard using event sourcing. They had a projection that aggregated customer usage statistics, billing history, and contract details into a single view. However, the projection logic was complex, involving several external API calls to retrieve real-time data from legacy systems and internal if-then-else statements to calculate loyalty points based on current system date. Consequences: inaccurate data. Loyalty points displayed on the dashboard were often inconsistent with the customer's actual balance because the projection wasn't idempotent and relied on the mutable external system time for calculations. Duplicate usage-increased events would sometimes double-count points. Corrupted rebuilds. When they tried to rebuild the dashboard projection from scratch after a major system upgrade, the rebuild would consistently fail or produce wildly inaccurate data after a few days because old events were being processed with new, time-dependent, point calculation logic, or the external API calls failed during the massive replay. Trust issues. Both customers and customer service agents lost faith in the dashboard's accuracy, leading to increased support calls and manual checks. Resolution. ConnectCo tackled this by making the projection idempotent. They stored a unique usage evented and used UPSERT logic for usage stats to prevent double counting. Loyalty points became a separate, aggregated value based on loyalty points earned events, which were fully contained facts, rather than being recalculated by the projection itself. Removing external dependencies from the projection. All data needed for the projection was made available within the event itself or derivable purely from the event stream. Simplifying projection logic. The projection's responsibility was reduced to simply taking an event and transforming its data into the read model structure. All complex business logic like loyalty point calculations moved back to the aggregates, right side, where loyalty points earned events were first emitted. Implementing a robust rebuild process. They streamlined the rebuild process, using batch processing and ensuring that the projection could be run deterministically against the entire event stream. This significantly improved the accuracy and reliability of their customer dashboard, rebuilding trust in the system and reducing operational burden. 6.6 Key takeaways for robust query models. Projections are essential for efficient queries in event-sourced systems, but they are also a common source of bugs and inconsistency. To avoid projections gone wild, idempotency and rebuildability are non-negotiable requirements for all projection logic. Projections are tools for RED optimization and data transformation, not for complex business logic execution. Keep them dumb and data-focused. Design your read models with the specific consumer queries in mind, and be prepared to create multiple specialized projections if necessary. Rigorous testing, especially focused on replay scenarios and idempotency, is crucial for building trust in your read models. Chapter 7. The Event Store as Your Only Data Store. Misinterpreting the source of truth. We've seen how proper event design and projection management are critical. Now, let's confront another common and often fundamental misunderstanding that undermines the efficiency and scalability of an event-sourced system: treating the event store as a general-purpose relational database, or attempting to use it as the sole data store for all system data and queries. This anti-pattern fundamentally misinterprets the event store's specialized role as the source of truth for a sequence of facts. 7.1. What is the event store as your only data store anti-pattern? This anti-pattern occurs when developers try to perform complex queries, aggregations, or arbitrary lookups directly against the raw event stream stored in the event store. Instead of leveraging dedicated read models, projections, built specifically for query optimization, the event store is burdened with requests for operational data or analytical reports that it is simply not designed to handle efficiently. Examples of this anti-pattern include attempting to find all active customers by scanning every customer-created and customer-deactivated event in the entire event store, trying to get the last 5 orders from a specific product category by filtering the main event stream for order-placed events and looking inside their payloads, running complex join-like operations, e.g., all orders placed by customers who signed up in the last month directly against event data. Using SQL-like query languages directly on the event store for general-purpose application queries. Imagine if, to find out your current bank balance, you had to manually sift through every single transaction slip you ever received since your account opened, add up credits, and subtract debits. Then, if you wanted to know your average spending last month, you'd have to find all slips from that month and perform the calculation. This is what it's like trying to query an event store as a general-purpose database. While the event store is the authoritative source of truth for the sequence of events, it is not the ideal store for arbitrary current state queries. 7.2. Symptoms and consequences. The belief that the event store can serve as an all-in-one solution leads to severe performance and operational issues. Extremely slow queries. The core design principle of an event store is optimized for sequential append operations and efficient retrieval of an aggregate-specific event stream. It is typically not indexed for arbitrary field-based lookups, filtering across multiple streams or complex aggregations. Attempts to perform such queries result in table scans or similar full-stream reads, leading to prohibitively slow response times, especially as the system scales. High operational load on the event store. Burdening the event store with every single read query strains its resources, potentially impacting the write performance, its primary function, and overall system availability. It becomes a bottleneck, defeating the purpose of separating concerns. Developer frustration and complexity. Developers struggle to write efficient queries against an unsuitable data structure. They might attempt to build complex, custom indexing layers on top of the event store, leading to brittle code and increased maintenance overhead. Data structure mismatch. Event streams are inherently denormalized facts laid out chronologically. They lack the indexing, join capabilities, and optimized query planners found in relational databases or specialized query stores. Scalability bottlenecks. The event store can become a single point of failure and contention if both write append and read query operations heavily contend for its resources. This undermines the scalability benefits promised by a CQRS-based event sourcing architecture. Increased infrastructure costs. To compensate for poor performance, you might be forced to provision overly powerful and expensive event store infrastructure, while a different, cheaper database would have done the job better for queries. 7.3 Root causes of this anti-pattern. This anti-pattern primarily stems from misunderstanding the event store's purpose, a fundamental lack of clarity about what an event store is designed for. It's the source of truth for sequence of facts, a robust audit trail, and the foundation for rebuilding state, but not a replacement for diverse data query patterns. Skipping or underestimating CQRS. The event store as only data store, anti-pattern, is often a direct consequence of failing to fully embrace or implement CQRS, command query responsibility segregation. Without a clear separation of write and read models, the tendency is to force all data operations through a single, ill-suited interface. Desire for simplicity, false economy. Developers might try to avoid the perceived complexity of maintaining separate read models and database technologies. However, this simplicity, upfront, quickly leads to insurmountable operational complexity and technical debt down the line. It's a classic example of premature optimization in reverse, avoiding necessary complexity that enables scalability and clarity. Event sourcing is the database mentality. While event sourcing is an architectural style that influences your data strategy, the event store itself is best viewed as a specialized ledger, not a universal data management system. 7.4 Strategies to avoid misusing the event store. To leverage the event store effectively and avoid the severe consequences of this anti-pattern, adhere to these strategies. Strict adherence to CQRS. This is arguably the most critical strategy. The event store is the authoritative source for the right model. It is where all commands are processed and events are appended. Its job is to capture what happened. Always derive data for querying into dedicated read models, projections. These read models are purpose-built for specific queries and stored in databases optimized for those queries. Their job is to answer what is. This separation allows you to optimize each side independently. High write throughput for the event store and highly performant reads from your various read models. Choose the right tool for the read model. Different query needs demand different database technologies. Relational databases, e.g., PostgreSQL, MySQL, SQL Server, excellent for complex transactional queries, joins, and highly structured data. Use them for generalized application queries where a normalized or denormalized relational view is best. NoSQL document databases, e.g., MongoDB, Couchbase. Great for flexible schemas, denormalized data, and high-velocity reads of single documents, suitable for specific views or user profiles. Search engines, e.g., Elasticsearch, Solr. Ideal for full-text search, complex aggregations, and analytical dashboards. Key-value stores, e.g., Redis, Cassandra, for very high-throughput, simple key-value lookups. Data warehouses, data lakes, for long-term historical analysis and business intelligence, often built from events. Event store for write model only, almost exclusively. Its primary functions are twofold: appending new events, storing the immutable history, retrieving an aggregate's full event stream, for reconstitution during command processing. Queries directly against the event store should be limited to these highly optimized operations or very simple lookups of event metadata, e.g., get all streams for user X. If the event store implementation specifically supports and optimizes them. Educate the team. Ensure all developers and architects understand the distinct roles and strengths of the event store versus various read models. This mindset shift is crucial. Conducting workshops and setting clear architectural guidelines can help prevent this anti-pattern. 7.5 Case study anecdote. The reporting system built on raw event streams. Dataco, a data analytics startup, wanted to build a real-time dashboard for their customers. showing active user counts, feature usage, and conversion funnels. Being enthusiastic about event sourcing, their initial approach was to build complex SQL-like queries directly against the event store. They had events like user signed up, page viewed, feature used, product purchased. Consequences, dashboard loading times. The dashboard, which required aggregating data across millions of events, took minutes, sometimes hours, to load. This was unacceptable for a real-time application. Operational strain. Running these analytical queries put immense pressure on the event store, leading to increased latency for critical write operations, user signups, product purchases. At peak times, the entire system would slow down. Scaling woes. They kept throwing more expensive hardware at the event store, but the fundamental inefficiency of querying a sequential log like a relational database persisted. Debugging difficulty. Even simple report discrepancies were hard to debug, as the event store didn't provide standard query profiling or indexing capabilities for their ad hoc analytical queries. Resolution. After a painful few months, Dataco realized their mistake and refactored their system to fully embrace CQRS. They kept the event store as the immutable source of truth for all events. They introduced a dedicated analytics database, e.g., a columnar store or a data warehouse, for their dashboard data. They created several specialized projections that consumed events from the event store and transformed them into pre-aggregated, denormalized tables optimized for the specific dashboard queries. A daily active users projection would increment a counter for each user signed up or page-viewed event. A conversion funnel projection would update stages based on page-viewed and product-purchased events. These projections ran asynchronously, ensuring that the event store remained performant for core business operations. The dashboard then queried these highly optimized analytical read models, resulting in sub-second load times. This significant architectural shift rescued Dataco's real-time dashboard and allowed their core event source system to scale without disruption. 7.6 Key takeaways for data storage roles. The event store is a uniquely powerful component in an event source system, but it is a specialized tool, not a universal one. The event store is your reliable, append-only ledger for all facts. It is not a general-purpose query database. Separate your write concerns, event store, from your read concerns, read models projections, rigorously through CQRS. Choose the optimal database technology for your specific query patterns on the read side. Don't try to force a single hammer for all nails. Chapter 8, Temporal Trauma. Handling Schema Evolution and Time Travel Challenges. By now, you should have a solid grasp of sound event modeling, inter-service communication, and the critical role of projections and the event store. However, one of the most significant and often underestimated challenges in event sourcing lies in navigating the passage of time. Temporal trauma. This anti-pattern refers to the difficulties encountered when evolving event schemas, managing historical data, and correctly replaying events in a system where the rules of the domain might change. 8.1 What is the temporal trauma anti-pattern? The temporal trauma anti-pattern specifically arises from breaking changes in event schemas, modifying the structure, fields, data types of an event in a way that makes older versions unreadable or incompatible with newer code. This means that when you try to replay historical events, which are designed to be immutable and never change, the system chokes because it expects a different format. Ignored event versioning. A lack of a clear, deliberate strategy for how event schemas will evolve over time. This leads to ad hoc, brittle solutions when changes become unavoidable. Attempting to mutate historical events, confusing the immutability of the event with the mutability of its interpretation. Some developers try to go back and modify past events to fit new rules or correct perceived errors, which is a cardinal sin in event sourcing. Challenges with time travel logic. When the business rules themselves change throughout time, e.g., how a loyalty discount was calculated in 2018 is different from 2023. Simply replaying old events with current business logic yields incorrect results. Imagine a historical archive where documents are constantly rewritten in new languages or formats without any translation guide. Or a history book where past events are edited to fit current political narratives, making the original context and truth impossible to decipher. This is the essence of temporal trauma. 8.2 Symptoms and Consequences. The impact of temporal trauma can be profound and paralyzing for a long-lived event source system. Inability to replay old events. This is the most critical symptom. Core event sourcing benefits, like rebuilding contaminated read models, performing data migrations, or debugging by reconstructing state, become impossible or generate erroneous results. Running a new projection on an old event stream simply breaks. Errors during replay reconstitution. The system crashes or throws exceptions when trying to process older events, leading to a breakdown in historical integrity. Need for complex and brittle migration scripts. Instead of elegant schema evolution, teams resort to one-off, dangerous, and hard-to-maintain scripts that attempt to convert old event data, often directly manipulating the event store. Difficulty introducing new features. If new features rely on a consistent understanding of historical data, schema evolution barriers can block progress. Fear of change rigidity. Development teams become terrified of changing event schemas, leading to stagnation, workaround solutions e.g., jamming new data into existing fields, and ever-increasing technical debt. This contradicts the agility ease is supposed to provide. Compromised data integrity. If historical data cannot be reliably replayed or interpreted, the system's audit trail loses its integrity, undermining trust in the system's veracity. 8.3 Root causes of this anti-pattern. Temporal trauma is rarely malicious. It usually stems from misunderstanding events are immutable, interpreting immutability to mean event schemas can never change. While the recorded instance of an event is immutable, its definition or schema will inevitably evolve as a business grows. Lack of a clear versioning strategy, failing to anticipate and plan for event schema evolution from the project's inception. Ad hoc fixes are attempted only after a breaking change occurs, directly binding internal models to event schemas. Using the raw event structure as the domain model within services, making any event change ripple directly through the internals of consuming applications. Not considering backward-forward compatibility. Designing new event schema versions without thought for how older consumers will interpret them, or how new consumers will handle older events. Underestimating time travel implications. Understating the challenge that business rules themselves can evolve. For example, if a loyalty point calculation changes, simply replaying old purchase-made events through the new calculation logic yields incorrect historical loyalty points. Attempting to mutate past events. The mistaken belief that an incorrect event, payment failed when it succeeded, can be changed retroactively, violating the append-only principle. 8.4 Strategies to avoid temporal trauma. Navigating temporal evolution requires deliberate planning and robust mechanisms. The following strategies are crucial. Implement a robust event versioning strategy. This is paramount. The goal is to allow new event producers to publish new versions while older consumers, or replay mechanisms, can still correctly interpret historical event versions. Upcasting migration functions, the most common and recommended approach. When reading events from the event store, e.g., for aggregate reconstitution, projection building, or replay, intercept old event versions and transform them on the fly into their latest version using specific transformation functions, upcasters. Example: if user-registered v1 had first name, last name, and user-registered v2 added full name, your upcaster would take a v1 event, compute full name from first name and last name, and return a v2 event. Event transformers migrators, offline. For extremely rare, large-scale, or breaking changes that cannot be handled by upcasters, you might need an offline process that reads and rewrites a portion of your event stream into a new format in the event store. This is complex and should be avoided if possible. Backward compatibility first, always strive to make new versions of events backward compatible. This means adding new fields. Keep them optional or provide default values so older consumers don't break. Never removing fields that existing consumers rely on. Renaming fields. Treat this as adding a new field and deprecating the old, typically handled with an upcaster. Separate event schema from internal models. Use a translation layer, e.g., dedicated DTOs or mappers, between the raw event schema and your service's internal domain models. This insulates your code from direct event schema changes, allowing you to adapt internal models without immediately breaking with old event versions. Never mutate or delete past events. This is the golden rule. Events are immutable historical facts. If a correction is needed, e.g., an order was accidentally canceled, don't change the order canceled event. Instead, emit a new compensating event like order restored. The sequence of events should tell the full story, including errors and corrections. Plan for business rule evolution, dealing with true time travel. Sometimes, the meaning or processing of events changes over time, e.g., tax laws change, loyalty program rules evolve. Replaying old events through new business logic will yield incorrect results. Version business logic. Design your logic to be versioned. When applying a calculation, e.g., calculate loyalty points for this order, ensure you use the rule set that was valid at the time the order was placed. This often means storing the version of the rule applied or having versioned aggregate implementations. Snapshotting aggregates. While not a versioning strategy itself, strategically taking snapshots reduces the number of events that need to be replayed, potentially limiting the exposure to historical event versions. Test replays and schema evolution. Include tests that specifically validate how your system handles older event versions and full historical replays. This proactive testing is essential to prevent deployment surprises. 8.5 Case Study Anecdote. The customer address change that broke the world. Globoship, an international logistics company, used event sourcing to track packages. When they launched operations in new countries, they updated their delivery address updated event schema to include a country code field, which was crucial for routing. Their previous delivery address updated events did not have this field. They deployed the new code without implementing any upcasting or versioning strategy. Initially, production worked fine because new events were immediately in the new format. Consequences: broken analytics and read models. When their analytics team tried to rebuild a large delivery projection used for optimizing delivery routes from the entire historical event stream, it started crashing. The projection code expected the country code field in every delivery address updated event. Old events, lacking this field, caused deserialization errors. Historical data loss. Because the projection couldn't process old events, they effectively lost the ability to use historical delivery data for route optimization and performance analysis for package changes prior to the country code deployment. Debugging nightmare. When a customer queried an old delivery, the system sometimes failed to reconstruct the address correctly because it couldn't reliably process the old delivery address updated events. Resolution. Globoship implemented an upcaster for their delivery address updated event. This upcaster intercepted V1 events without country code, looked up the country code based on the provided address, e.g., from the postal code or city, and transformed the V1 event into a V2 event with the correct country code before it was processed by the projection or aggregate. V2 events were passed through untouched. This simple yet powerful mechanism allowed them to successfully rebuild their analytics projections from the complete history, ensure that querying old delivery data worked without issues, regain confidence in their event sourcing implementation's ability to evolve. 8.6 Key takeaways for future-proofing events. Temporal trauma is a significant challenge in event sourcing, but it is manageable with forethought and the right strategies. Events are immutable statements of fact, but their schemas, definitions will evolve, and their interpretation can change over time. Plan for event schema changes from the very beginning. Don't wait for a crisis. Embrace event versioning strategies, especially upcasting, to gracefully handle older event formats. Never modify history. If a correction is needed, emit a new compensating event that clearly records the correction. Be mindful of truly time-dependent business rules and version your logic or data accordingly. Chapter 9. The Stateful Subscriber. Breaking idempotency and immutability. In previous chapters, we've covered the crucial role of events as immutable facts and the necessity of well-designed projections. Now, we turn our attention to the processing of events by downstream consumers, specifically the critical concept of idempotency. The stateful subscriber anti-pattern directly violates this principle, leading to data inconsistencies, incorrect business processes, and significant operational headaches. 9.1 What is the stateful subscriber anti-pattern? The stateful subscriber anti-pattern describes an event consumer, a subscriber or handler that is not idempotent. The subscriber performs an action or updates its internal state in a way that produces a different and usually incorrect result if the same event is processed multiple times. Maintains its own mutable state externally. The subscriber relies on external mutable shared state, e.g., an in-memory cache, a non-transactional database connection, or a global variable that is not consistently updated or properly handled under retry scenarios. Introduces uncontrolled side effects. The subscriber performs actions like sending emails, making API calls, or initiating financial transactions multiple times for a single logical event. Imagine if pressing the print button on a receipt printer sometimes printed one copy, but if there was a network glitch, it might print 2 or 3, and each led to a new charge. Or a factory worker who, after inspecting a product, decides to package it, but if asked to inspect the same finished product again, packages it a second time. This is the essence of a stateful, non-idempotent subscriber. 9.2 Symptoms and consequences. The consequences of non-idempotent or overly stateful subscribers are severe and directly impact data integrity and system reliability. Duplicate data and inconsistent read models. If an event message is redelivered, a common occurrence in distributed systems due to network issues, retries, or consumer restarts, a non-idempotent subscriber will create duplicate entries in its database or update existing data incorrectly. For example, a payment received event processed twice could apply the payment twice to an account balance. Incorrect business processes. Critical business actions are performed multiple times. Examples include sending duplicate confirmation emails, processing double charges, issuing multiple refunds, or creating multiple entries in a tracking system. Difficult recovery from failures. When a service crashes and restarts, message queues often redeliver unacknowledged messages. If the subscriber isn't idempotent, this leads to a flood of erroneous operations upon recovery. Non-deterministic system behavior. The outcome of an operation becomes dependent on the precise timing and number of event deliveries, rather than the intrinsic business logic. This makes debugging incredibly painful, as issues might not consistently reproduce. Complex debugging, tracing down why data is incorrect or why an action was performed multiple times, becomes a forensic exercise, often taking significant development time to resolve. Compromised reliability and trust. Users lose trust in the system's accuracy, leading to increased support calls, manual data corrections, and ultimately, reputational damage. 9.3 Root causes of this anti-pattern. This anti-pattern primarily stems from misunderstanding message delivery semantics. Most message brokers and distributed systems guarantee, at least once, delivery, not exactly once. This means an event might be delivered multiple times. Developers often implicitly assume exactly once delivery and don't design for message redelivery. Ignoring network guarantees and failure scenarios, not designing for the realities of distributed computing network partitions, service crashes, timeouts, and retries. Lack of explicit idempotency design, failing to build idempotency checks into event handlers and subsequent operations. Reliance on external mutable state, using global caches, non-transactional resources, or poorly synchronized external systems that lead to inconsistent state across retry attempts. Treating event handlers as simple function calls. Thinking of an event handler as a simple function that executes once without consequence, rather than a component in a distributed, eventually consistent system. 9.4 Strategies to avoid the stateful subscriber. Designing for resilience in an event-source system means proactively building idempotency into every event consumer. Here are key strategies. Design for idempotency from the start. This is the most crucial principle. Ensure that processing the same event multiple times yields the same result as processing it just once. Always track processed event IDs, the simplest and most effective technique. When an event is consumed, store its unique message ID, often provided by the message broker or the event itself, in a durable store, e.g., a database table, a dedicated idempotency store, before performing the action. Before processing any event, check if its ID has already been recorded. If so, skip processing, otherwise, record the ID and proceed. This should ideally be within a transaction that includes the action and the state change for atomicity. Semantic idempotency in operations. Design the operation itself to be repeatable without creating side effects. For creating resources, use insert if not exists or check for existence before inserting. For updating resources, use UPSERT operations, update if exists, insert if not, on your read models. For specific fields, only update if the new value is different or based on a version number. For decrementing incrementing counters. If a simple ++ or leads to issues on replay, store the actual value from the event and calculate the new total equals old total plus event delta, then apply the new total value to the record for idempotency. For external API calls notifications. Implement a deduplication mechanism on the receiving end if possible, or include unique correlation IDs in your requests to external systems that allow them to handle duplicates. Transactional outbox pattern for publishing events. While this primarily addresses publishing without losing events, it also implicitly supports idempotency. By ensuring events are only published after a command's changes are committed to the event store within the same transaction, you avoid situations where events are published without the corresponding state change being recorded. Embrace eventual consistency. Understand that immediate, global consistency is not possible in distributed systems. Design your business processes and user interfaces to gracefully handle the temporary discrepancies that might arise, knowing that the system will eventually converge to a consistent state. Robust error handling and retries. Implement dead letter queues and retry mechanisms for failed event processing, but always ensure these retries are built on an idempotent foundation. If a retry attempts to process a message that already succeeded but failed to acknowledge, idempotency prevents damage. Avoid shared mutable state. Subscribers should process events based on the event's data and build their own state within their own transactional boundaries. If shared state is absolutely necessary, it must be managed with robust concurrency controls and consistency guarantees equivalent to those provided by the event store for aggregates. 9.5 Case Study Anecdote. The double email confirmation nightmare. Mailwise, a new email marketing platform, used event sourcing to track campaign activity. When a user scheduled a campaign scheduled event, an event handler was supposed to send a confirmation email. The system used a standard message queue with, at least once, delivery semantics. Consequences. One day, due to a transient network glitch between the message queue and the email sending microservice, some campaign-scheduled events were redelivered. Duplicate emails. Users started receiving 2 or 3 identical campaign confirmation emails for the same campaign. Customer confusion and support overload. Customers were confused, reporting duplicate emails, leading to a flood of support tickets. Damaged reputation. Mailwise started to get a reputation for being unreliable and spammy. Root cause. The email confirmation handler simply triggered the email sending service whenever it received a campaign-scheduled event. There was no internal mechanism to check if an email for that specific campaign schedule had already been sent. It was a classic non-idempotent operation. Resolution. Mailwise implemented an idempotency check in their email confirmation handler. They added a sent campaign confirmation table with a unique constraint on campaigned and scheduled at, or simply campaign scheduled evented. Before sending the email, the handler would attempt to insert a record into this sent campaign confirmation table. If the insertion succeeded, meaning it was the first time this specific event was being processed, it would send the email. If the insertion failed due to a unique constraint violation, meaning the email had already been triggered by a previous processing of the same event, The handler would simply do nothing and log that the event was a duplicate. This simple change ensured that even with, at least once, delivery, only one confirmation email was ever sent per unique campaign-scheduled event, restoring customer trust and reducing support tickets. 9.6 Key takeaways for resilient event handling. The stateful subscriber anti-pattern highlights the critical importance of idempotency in distributed, event-driven architectures. Assume at least once message delivery. Never assume exactly once. Design all event consumers to be idempotent. Event handlers should primarily be stateless or maintain state in a deterministic and reconstructible manner, always ensuring that repeated processing of the same event yields the same outcome. Robust error handling combined with unwavering adherence to idempotency is the bedrock of system reliability and data consistency in event sourcing. Chapter 10. Event Sourcing Testing Anti-Patterns. Ensuring System Health. We've now covered several critical anti-patterns related to event modeling, inter-service communication, and event processing. However, even the most meticulously designed event source system can falter without a robust testing strategy tailored to its unique characteristics. The event sourcing testing anti-patterns described in this chapter highlight common mistakes in validating event source systems, often leading to brittle tests, missed bugs, and a lack of confidence in deployments. 10.1 What are event sourcing testing anti-patterns? This anti-pattern manifests when testing strategies for event source systems, over-reliance on end-to-end tests, treating highly integrated, slow, and brittle end-to-end tests as the primary validation mechanism, neglecting faster, more focused unit and integration tests. Testing like a CRUD app. Applying testing techniques suitable for traditional CRUD applications, e.g., directly querying a database for state changes after an action to event source systems, which are fundamentally different commands in, events out. Ignoring aggregate behavior. Not adequately testing the core business logic within aggregates, which is responsible for enforcing invariance and emitting events. Inadequate projection testing. Failing to properly test projections for correctness, idempotency, and their ability to accurately rebuild read models from historical events. Brittle or inconsistent tests. Tests that break frequently due to minor changes, or where the outcome is not deterministic, leading to flaky tests that erode developer trust. Undertesting event contracts. Not validating the schema and meaning of events exchanged between different services or bounded contexts, leading to unexpected breakages when one service changes its event structure. Imagine trying to test the reliability of a complex machine by only observing its final output, without ever checking its internal components or the logic of individual gears. Or building a test environment that's more fragile and prone to failure than the system it's meant to validate. 10.2 Symptoms and Consequences. The impact of inadequate or flawed testing in event sourcing is significant. Brittle and high-maintenance tests, tests that are difficult to write and maintain, requiring constant updates even for minor code changes, leading to developer frustration and a reluctance to refactor. Slow feedback loops. Over-reliance on slow integration and end-to-end tests elongates development cycles, making it harder to iterate quickly and introduces friction in continuous integration, continuous delivery pipelines. Missed bugs and production issues. Insufficient coverage of core logic, especially aggregate invariance or projection accuracy, leads to defects slipping into production, resulting in customer impact and costly fixes. Low confidence in deployments. Developers and operations teams lack confidence in releasing new features or bug fixes, leading to risk aversion and slower deployments. Difficulty replicating production issues. Without proper testing strategies and tools, e.g., event replay capabilities, it becomes incredibly challenging to replicate specific production issues in a controlled test environment. High operational cost. Constant firefighting of production bugs, manual data fixes, and complex rollbacks contribute to increased operational overhead. 10.3 Root causes of this anti-pattern. Event sourcing testing, anti-patterns typically arise from misunderstanding event sourcing's testable nature. not recognizing that event sourcing intrinsically provides powerful hooks for testing due to its deterministic, commands in, events out nature for aggregates, and the reconstructible nature of projections. Over-reliance on external dependencies. Coupling tests too tightly to actual databases, message queues, and external services, making tests slow, brittle, and non-deterministic. Insufficient focus on aggregate logic. Neglecting to thoroughly test the core business rules that govern state transitions and event emission within aggregates. Underestimating projection complexity. Overlooking the need for comprehensive tests around projection accuracy, idempotency, and rebuildability. Lack of a clear testing strategy. Failing to define a comprehensive test, pyramid, or similar strategy that leverages different types of tests for different levels of the system. Ignoring event immutability and consistency. Not designing tests to specifically validate how the system handles event versioning, eventual consistency, and message redelivery, idempotency. 10.4 Strategies to avoid testing anti-patterns. Effective testing in event sourcing leverages its unique characteristics to provide high confidence with fast feedback. A multi-layered approach is key. 1. Aggregate unit testing, given when, then. This is the foundation and provides the fastest feedback. Principle: test the aggregate's behavior in isolation, mimicking its interaction with commands and events. Structure: use a given when then style. Given, an initial state of the aggregate represented by a sequence of past events. When, a specific command is applied to the aggregate. Then, assert that the aggregate emits the expected new events and no unexpected ones, and that its internal state, if accessible for testing, correctly reflects the changes. Benefits: fast, deterministic, isolated from external dependencies, provides high confidence in core business logic. This is where the majority of your unit tests should reside. Example: given order created, D customer, item added ID product A, when add item ID product B2, then item added, ID product B2. 2. Projection integration testing. Principle: validate that projection handlers correctly transform event streams into the desired read model state. Method: provide a sequence of events to the projection handler. Assert the resulting state in the read model, e.g., a database table, a document store. Crucially, include tests for idempotency. Processing the same event twice should yield the same result, and rebuild scenarios. Dropping the read model and replaying the entire event stream should produce the correct final state. Benefits: confirms read model accuracy, validates transformation logic, ensures rebuildability. These tests are typically slower than aggregate unit tests as they involve a database. 3. Event handler subscriber unit integration testing. Principle: test that individual event handlers correctly perform their side effects or consume events reliably. Method: feed test events to the handler and assert its outcomes, e.g., a mock API call was made, a specific message was sent. Focus on ensuring idempotency in these handlers. Mock external dependencies as needed. Benefits: validates the reaction logic to events, ensures external interactions are correct and repeatable. 4. Contract testing for events. Principle: ensure that events published by one service producer are compatible with the expectations of other services, consumers. Method: use tools like Pact to define contracts between event producers and consumers. The producer's tests verify it adheres to the contract. The consumer's tests verify it correctly processes events according to the contract. Benefits: prevents breaking changes in distributed, event-driven systems, fosters independent deployment. 5. Strategic use of end-to-end system tests. Principle: use sparingly for critical user flows that traverse multiple services. These are expensive and brittle. Method: focus on validating the system's external behavior from a user's perspective, rather than trying to test every internal component. Benefits: provides a final sanity check that all components work together in a deployed environment. 10.5 Case study anecdote. The green build, broken production syndrome. Build Fast, a software development company, prided itself on its automated CI/CD pipeline. For their new product, built with event sourcing, their testing strategy primarily relied on a comprehensive suite of end-to-end E2E UI tests. These tests would simulate user interactions, verify UI elements, and check the database state at the end. Their E2E tests were extensive, and their CI pipeline often showed a green build. Consequences: slow feedback. The E2E test suite took over 2 hours to run, significantly delaying feedback to developers. False confidence. Despite green builds, production would frequently encounter subtle data integrity issues or incorrect calculations in user-facing dashboards. For example, loyalty points were sometimes miscalculated, or order statuses didn't update correctly. Debugging nightmare. When a production bug occurred, it was incredibly hard to reproduce and isolate. The E2E tests were too high-level to pinpoint the exact failing aggregate logic or projection error, and there were no lower-level tests to guide the debugging process. Brittle tests. The E2E tests were highly sensitive to minor UI changes or test data variations, leading to frequent, flaky failures that eroded developer trust. Resolution. Buildfast realized their mistake. Their E2E tests were passing only if the UI looked correct, but failed to validate the underlying event processing logic. They reformed their testing strategy, prioritized aggregate unit tests. They invested heavily in writing fast, deterministic aggregate unit tests using the given-when-then approach. These tests quickly caught errors in business rules and event emission. Introduced projection integration tests. They added tests that fed various event sequences to their projections, verifying that the read models were accurately and idempotently updated. This caught the loyalty point calculation and order status update issues. Implemented contract tests. For events crossing microservice boundaries, they used contract testing to ensure consumer compatibility. Reduced E2E tests. Kept a smaller, critical set of E2E tests for the most vital user journeys, running them less frequently. This shift dramatically improved their bug detection rate, sped up their feedback loops, and gave developers genuine confidence in their releases. The system still had E2E tests, but they were no longer the sole, or even primary, source of truth for system health. 10.6 Key takeaways for confident testing. Event sourcing provides inherent advantages for testing that should be leveraged. Embracing these strategies will lead to a more robust, maintainable, and trustworthy system. Build a robust test pyramid. Prioritize fast, deterministic unit tests for aggregates, your core business logic, followed by targeted integration tests for projections and event handlers, and a minimal set of end-to-end tests. Test for idempotency and rebuildability as a first-class concern in your projection and handler tests. Contract testing is essential for maintaining compatibility in distributed event source systems. Embrace the commands-in, events-out nature of aggregates for highly effective and deterministic unit testing. Chapter 11, Beyond Anti-Patterns, Building Resilient and Future-Proof Event Source Systems. We've now journeyed through the primary anti-patterns that plague event sourcing implementations, from the overly granular mono-event to the sprawling big event, from the suffocating Chatty system to the inconsistent projections gone wild, and from the misguided event store as only data store to the crippling temporal trauma and stateful subscriber flaws, finally culminating in the pitfalls of event sourcing testing anti-patterns. Each chapter has highlighted a common misstep and offered clear strategies for avoidance. 11.1 Recalibrating our understanding. Key lessons learned. Let's briefly recap the core principles that emerged as crucial counterpoints to these anti-patterns. Events as immutable facts. Events must represent meaningful, past-tense business occurrences, not mere data changes. Once recorded, they are immutable and serve as the definitive ledger of history. CQRS is foundational. The strict separation of write concerns, using an event store for aggregates, and read concerns, using dedicated read models projections, is not optional but essential for scalability, performance, and flexibility. Idempotency is non-negotiable. Any event consumer, especially projections and handlers performing external actions, must be designed to produce the same result regardless of how many times an event is processed. Strategic event granularity. Events must be specific enough to convey clear business intent, avoiding big events. yet broad enough to represent logical business actions, avoiding mono-events. Bounded contexts dictate communication. Inter-service event communication must be disciplined, representing well-defined contracts between contexts, avoiding overly chatty systems. Evolution is inevitable. Plan for it. Event schemas will change, and business rules will evolve. Robust versioning strategies, especially upcasting, are critical for long-term viability. Test appropriately. Leverage the deterministic nature of event sourcing for focused aggregate testing and ensure projections are thoroughly validated for accuracy and rebuildability. Event sourcing is not merely a database choice. It is a fundamental architectural style that impacts every layer of your application design and development process. 11.2. The holistic view. Designing for longevity and adaptability. Moving beyond simply avoiding anti-patterns. Truly resilient and future-proof event-sourced systems are built upon a holistic understanding of software design principles. Domain-driven design, DDD. The concepts of bounded contexts, aggregates, and a well-defined ubiquitous language are not just complementary to event sourcing, they are foundational. They help you carve your system into manageable parts, define clear responsibilities, and ensure events reflect true business meaning. Event storming. This collaborative workshop technique is invaluable for discovering the critical events, commands, and aggregates in your domain. It actively involves domain experts and technical staff, fostering a shared understanding that is crucial for effective event sourcing. Embrace eventual consistency. Moving away from the synchronous, transactional mindset of traditional systems is challenging. Event sourcing fully embraces eventual consistency. Design your system, including your user interface and business processes, to operate effectively with this reality. Clearly communicate the eventual consistent nature to stakeholders and users. Modularity and decoupling. Event sourcing naturally promotes loose coupling between components as they primarily communicate via immutable events. This modularity allows for independent evolution and deployment of services, a key benefit in microservices architectures. Design your system boundaries carefully and stick to them. 11.3. When event sourcing is and isn't the right choice. While powerful, event sourcing is not a universal panacea. It introduces complexity, and its benefits must outweigh these costs for your specific use case. Consider event sourcing when you need a complete, unalterable audit log of every change. You require temporal queries or the ability to time travel to reconstruct historical states, e.g., for debugging, analytics, or regulatory compliance. Your domain is complex with rich behaviors and invariants that are naturally expressed as a sequence of events. You need high write scalability where pure appends can be optimized. You want strong decoupling between different parts of your system, especially in a microservices context. You anticipate extensive data analysis or machine learning capabilities based on historical events. Reconsider event sourcing when your application is a simple CRUD app with straightforward data entry and retrieval, where the added complexity offers little benefit. Your team lacks experience with this paradigm, and you don't have the resources for a significant learning curve. You require immediate, strong consistency across distributed contexts, though this can sometimes be mitigated with more advanced patterns. Your domain state changes frequently, but rarely needs auditing or historical reconstruction. Your project has extremely tight deadlines and resource constraints, as initial setup and design phases can take longer. It's a powerful tool, not a mandatory pattern. Thoughtful consideration of its applicability will save significant effort and frustration. 11.4. Operational excellence. Keeping event-sourced systems healthy. Building a resilient system also means ensuring its operational health. Event-sourced systems require particular attention, monitoring and observability, essential for distributed systems. Monitor event throughput, latency, and error rates from the event store, message queues, and individual event handlers. Track the health and freshness of your projections. Implement distributed tracing to follow a command through its event emissions and subsequent consumer reactions. Logging and alerting. Comprehensive logging of commands received, events emitted, and event handler processing is crucial. Configure alerts for deviations from expected behavior, such as message backlogs, failed event processing, or projection synchronization issues. Operational readiness for rebuilds. Practice and automate the process of rebuilding projections from scratch. Having a well-defined, performant, and tested rebuild procedure is your safety net against data corruption and schema evolution challenges. Capacity planning. Understand your event volume and data growth. Plan for event store storage, message queue capacity, and compute resources for event processing and projection updates as your system scales. 11.5. Continuous evolution and best practices. Software is never finished, it evolves. Event-sourced systems are no exception. Automated testing re-emphasis. As seen in Chapter 10, Automated Testing, especially unit tests for aggregates and integration tests for projections, is the bedrock of confidence in implementing changes and refactoring your event-sourced system. Documentation. Clear and concise documentation of event definitions, including their versions, bounded context boundaries, and architectural decisions, is invaluable for both new team members and for future maintenance. Consider tools that generate documentation directly from event definitions. Team education. Continuous learning and shared understanding within the team are critical. Regular discussions, workshops, and reviewing each other's designs consistent with event sourcing principles will raise the collective expertise. Refactoring. Don't be afraid to refactor event streams or redefine bounded contexts as your understanding of the domain deepens. While events are immutable, your interpretation and partitioning of them can and should evolve. Leveraging community knowledge. The event sourcing community is vibrant. Stay updated with new patterns, tooling advancements, and shared experiences from others navigating similar challenges. 11.6. The future of event sourcing. The principles of event sourcing are increasingly relevant in the modern software landscape. The rise of distributed systems, microservices, and real-time data processing has pushed events to the forefront of architectural design. Emerging trends include stream processing frameworks, technologies like Apache Kafka, Flink, and Kinesis, which are optimized for high-throughput, real-time event streams, continue to enhance the capabilities and accessibility of event sourcing. Cloud-native event stores. Managed cloud services are making it easier to deploy and scale event store implementations without managing the underlying infrastructure. Serverless and event-driven architectures. Serverless functions are a natural fit for event handlers, reacting to events without managing servers, further simplifying deployments and scaling. Real-time analytics and machine learning. The immutable, historical event stream is a rich source for training ML models, enabling real-time anomaly detection, personalized experiences, and powerful business intelligence. As data becomes more central to business strategy, and as architects continue to seek greater resilience and adaptability, the core tenets of event sourcing will only gain more prominence. 11.7 Conclusion. The journey continues. The event sourcing journey is challenging, requiring a significant shift in thinking from traditional state-based approaches. Yet, it offers profound rewards in terms of auditability, scalability, decoupling, and the ability to truly understand your business's history as a series of immutable facts. By understanding and actively working to avoid the anti-patterns described in this book, you are not just preventing problems. You are laying the groundwork for building robust, maintainable, and ultimately more valuable software systems. Armed with this knowledge, you are better equipped to navigate the complexities, make informed decisions, and leverage the full power of event sourcing. Go forth, design thoughtfully, learn continuously, and build the resilient systems of tomorrow.